Varignon theorem on moment of the resultant force. This is lesson number 217 from the book Mechanical Systems Calculations of the Marine Facilities. The theorem of Varignon on the moment of the resultant force. The moment of resultant of a special force system relative to any center is equal to geometrical vector sum of the moments of all force relative to this center. To explain this theorem, we can consider the mechanical body in the space, the special system, and the force applied the main resultant force. Main resultant are asterisk R0 asterisks, so the rotating moment 0. And when we move the resultant force to any other point, could be another point of rotation of the mechanical body. It can be a point A. The moment arises as well, so the transfer of the force to another point parallel on the parallel line of the action is corresponded with the rise of the rotating moment here on the figure 2.17.1. The rotating moment is vector moment m 0, 1 rotating moment. One of the consequences of the main resultant, or could be the assigned the resulting force and the resultant force and the resulting moment in the point 0, 1. To move it to the point 0, we can reduce the magnitude of the rotating moment to 0, vector moment. So this is about the transfer of the forces. But this resultant force is total of all forces acting on the mechanical system in the special state, indefinite one, not the flat state, but special one. And this is a theorem of the Varignon. Let me please repeat: the moment of the resultant of special force system relative to any center is equal to geometric sum of moments of all forces relative to this center. And we have the two versions of the Varignon theorem on the moment of resultant relative to an axis. Relative to an axis, we consider the rising moment of relative, just projection of the moment relative to the axis. So in the moment of the resultant force relative to any axis, what would be axis x1 is equal to the total of the projections of moments of all forces in the system caused the resultant force R0 asterisk. And this is in the case for the rotation around the axis, projection of the Varignon theorem on the axis x. And besides, we can have the Varignon theorem for the flat force system if we consider not the special state but the flat state on the plane. So the moments will not be the vector magnitudes, but it is the scalar magnitudes, and the moment relative definite point 0, 1 is of the resultant is equal to the moments relative this point on the plane of all the forces in the system caused this resultant force. And we had exercises. The first exercise 1. Determine the algebraic moment of the forces F and P of the assigned frame on the draft on the picture. Figure 2.17.2a. We have the forces F and P relative to the point A. So force F inclined to this beam, the up beam of the frame, inclined to angle alpha to the horizontal axis, and the force P applied to the vertical beam of the frame and applied it at the angle inclined gamma to the vertical axis. So how to do that? We know that the rotating moments algebraic because we consider the flat state. If it in the space could be vector moment, but in the flat it is a rotating moment only in of the efforts from within the plane. That's algebraic concept of the rotating moment. And this moment caused by two forces F and P. Forces are vectors because the two-dimensional space we have two axes X and Y, and there is vectors on the plane. Or we can do product the force on the arm. For example, we have force F minus force F magnitude multiplied by the arm HF. It's inclined arm. We don't know what is the arm of the force F. And the force P, magnitude P, inclined by the angle gamma to the vertical axis, and multiplied by HP. HP, we have the arm from the point A to perpendicular to the line of the action of the force P, but it could be the problematic to find the arm HP. So to simplify the assignment, we can just find the projections of the forces F and P. We consider these forces as a definite one resultant. The force F is the resultant of the force F1 horizontal component of force F and the vertical component F2. For these two components, we easily can find the arms of action of the moment rotation by these components related to the point A. For F1 component horizontal of the force F assigned, the arm is H. For the force F2, the arm is A. So we can do that as well for the other force P. We have a vertical component. Yes, P multiplied by cosine gamma, and this horizontal component P multiplied by by sine gamma. So after the substitute in the total of components of the rotation moment around the point A, so on behalf of force F, we have total of two components, MA of horizontal component of force F and the MA of vertical component of force F. This is a Varignon theorem used as this resultant F cause the same rotating moment around the point A as the components cause the same resultant moment total. So this is equal minus magnitude F multiplied by cosine alpha and by arm H minus F multiplied by sine alpha and by the arm A. These moments rotates clockwise, so we have two minuses. Therefore, the force P, the rotating moment of the force P around the point A is two components of rotating moment around the point A of the component of horizontal component and of the force P and the vertical component of the force P, and the rotating moment is equal. This one rotates counterclockwise. So, excuse me. This is horizontal component of P1, so it is by the sign rotate clockwise and with a minus sign and with a sign of the angle of inclination and the RB and plus rotating counterclockwise magnitude of P multiplied by cosine gamma and multiplied by L. So we found the rotating moment with not finding the arms of the forces themselves, but just the arms of the components of forces. Which of the components, which of these forces are the resultants. Another exercise, use of Varignon theorem to add two parallel forces to determine the resultant and the point of the application of the parallel forces. We have two parallel forces in the point A and B, and one parallel force and another one, F1 and F2, and we have to find the resultant and the point of the application. The resultant to find very easy, just any projection of vertical axis and the magnitude of resultant equal to magnitudes of force F1 and F2. But to do the Varignon theorem, we can consider that the resultant have to have the same rotating moment, for example, around the point zero, as two forces, the components of the resultant. And as we have zero, resultant moment is zero on the right, and the left we have the components of the rotating moment on behalf of the components of the resultant. And one rotates by the arm 0b, another one with 0a, and together one clockwise, another one counterclockwise. Sign rule here, we have a relative. Yeah, force F1 rotates clockwise, but in this kind of the balance equation, we can multiply both sides of the equation, multiply by both sides of the equation by -1, and this changes the signs in the equation, but do not put under doubt the correctness of the equation. So, considering this equation, we can originally, these two forces have to be equal to, and the proportion we can find of two forces are in the proportion of two parts of location of point zero. So what is the definition of the point of location of the resultant force? The definition is finding the proportion of the segments of A0 and 0B of the general segment AB to the point zero of location of point application of resultant force. The same we can do if these forces have the opposite direction. And we consider the same, we have the same proportion, and we have resultant force, which is the difference of two forces, F1 and F2. F1 is positive. We assume that the vertical axis directed upwards. So F1 minus F2 is the magnitude of the resultant. And relative definite point, we can find the proportion of 0b and 0a arms of the point of the application. You can see that the point application of the resultant is outside the segment which AB, which is the arm of the forces action relative to each other. Each is outside of the arm. Here we have inside, but this is two forces parallel vectors, collinear, but they are parallel and of the same direction as opposite. So the point application of the resultant force with not the rotating moment is outside the segment between these two forces application. Next exercise, the use of Varignon theorem for determining the resultant action line. So, okay, this is a resultant R1 asterisks, and we have the components of resultant R1x asterisk and one R1y asterisk. So we need to have the mathematical equation of this line. So the moment of a resultant relative the 0 point, relative 0 point is by these components, the difference, so first sum and the second one are product of the arm x by the projection vertical of the resultant R1 asterisk with a plus sign minus rotating clockwise product of the another one arm by the horizontal component of the resultant force. This is equation. We can exclude the symbolic description of the total of two moments of two components of the. Just consider the left and the right part, and this is a mathematical equation of the direct line. So the line equation we can a little bit simplify, and we can find that the dependence of the ordinate of the line of action of the force on the abscissa of the line of action of force is in this mathematical equation as the fraction of ry to rx fraction, yeah, by yx, and minus fraction of m0 divided by rx. And the questions and comments. Varignon theorem on the moment of the resultant. Excuse me. The moment of the resultant equal to the all to in the space is geometry, the vectors, a total of moments of all components of the resultant for the flat state is scalar. The scalar moment of resultant relative to any point of rotation on the plane is equal to the total of all forces components of the resultant relative to this point. 2.17.2, the connection between the main moments of the system of forces is relative the original and the new center. Here, connection, we when we consider two centers, this corresponds to the issue of the force transfer to the parallel line of the action, or coincide with the previous one line. And in this case, arises the rotation moment. So only one point is the point when we have no rotation moment, and if we move if we from this one point move the point of the application of force to parallel line, arises the rotation moment. The variant of 2.17.3 arises the variant of Varignon theorem for the moment of resultant relative to the axis. This is a projection of the resultant of moment of the resultant on the axis is equal to all projections of moments of the components of resultant to this axis. Here, Varignon theorem of plane system of force. The scalar form of Varignon theorem of plane system of force, a scalar moment of rotating of mechanical system in the plane. The scalar moment of resultant in the plane equal to scalar moments of all components of resultant in the plane. Excuse me. Application of Varignon theorem to decompose the force vector into component vectors. Yes, we can when we have to find. We decide the issues like to find the moment of rotation of force around definite one point. Sometimes this is more difficult issue to find the arm of rotation by this force directly around this point, but we can easily find the arms of rotation of the mechanical body around the point of rotation of the components, projections of this force on the axis abscissa and axis of ordinata, and maybe in the special state we can consider the rotation around the application. So we can instead of the rotation by the resultant force, consider the rotation by the components of resultant force. This is use of Varignon theorem. Determination of algebraic moment of forces about a point. This is like as well the use instead of the instead of finding out the arm of the rotation around the point on the flat, for example, on the plane, for example, we can consider the rotation by the components of the resultant force. Using Varignon theorem to add two parallel forces to determine the resultant and the point of its application. Sometimes to find the point of application of resultant for parallel forces is not obvious. So if the forces intersect, point of the intersection will be the application of the resultant. But if the forces are parallel, we can use the Varignon theorem to find the point of application. Usually we can easily find the magnitude of the resultant, but the point of the application, we need to consider the rotating moments under the impact of a resultant of the mechanical system or any other or body under action of the resultant. And on the other hand, we can consider the rotation of this body under the action of the components of the resultant. After that, we can find the resultant. We can find the arm of the action of the resultant. The arm of action of the resultant gives us the point of application of the resultant, because usually we have the rotation point, the point of the rotation of the mechanical body of the mechanical system. The use of Varignon theorem to create the line of action of the resultant. It's easy to find the line of action of the resultant if we know the resultant magnitude and we know the angle of the inclination of the resultant to the coordinate axis. If we have the resulting moment of all forces acting, so we can do the balance equation that the components of resultant on axis are equal to the rotation moment, and if we know the magnitude of the resultant as well, we can consider together as a balance equation. This balance equation is the linear equation on of dependence of ordinates of the line of action of the resultant on the abscissa, for example, on the flat state. Thank you very much.